Now that you've gotten some experience finding closed formulas for certain types of recursive sequences, we're going to find some more closed formulas for other types of recursively defined sequences. So the first thing we're going to do is learn how to recognize the recursive formulas for which our methods are going to work. We're going to take some guesses to find some of the solutions to the recursive formula. We're going to leverage those solutions that we find from our guesses to find more solutions, and then use those to find the appropriate formula for any given sequence. So the types of recursive formulas are the fancy names that I'm not going to make you memorize. I'm just going to let you know what they're called. They're called linear homogeneous recursive formulas. And they look like a sub n equals c1 times an minus 1 plus c2 times an minus 2, where the c's are constants, so c1 and c2. And actually, this is a special type of linear homogeneous recursive formula called a second order. Don't worry about that one. We just have to know what the recursive formulas look like for us. So an easy example is a sub n equals 5an minus 1 minus 6an minus 2. That one is linear homogeneous. But if we take that formula and just add a 1 at the end, that actually makes it not homogeneous. And that's only important to us because the techniques that we are going to learn would not be effective on that second sequence. So you might have noticed I haven't put any initial terms in there. We have each term in the recursive formula is based on the previous two, which means we have to have two initial terms. We're going to ignore those for now and just find sequences that satisfy the recursive formula. But we will get to the initial terms later once we do some analysis. So let's look at our example sequence. an equals 5an minus 1 minus 6an minus 2. So what we want to do is find solutions. Now there are often, as we've seen, systematic ways of finding solutions, but sometimes you just have to be good at making guesses. So you can actually, it's reasonable to guess lots of different types of sequences to see if they work, but it turns out that geometric sequences are the ones that are going to be the most productive. So we're going to look at sequences that look like a sub n equals r to the n, where r is some constant. We're not going to commit to that constant. We're not going to guess like 5 to the n or 10 to the n or 11 to the n. There are just too many that they could be. What we're going to do is say r to the n and see if we can find a backdoor way of figuring out what that r is. So we're going to look to find r by plugging it in. Now a sub n equal r to the n means that n in the subscript is the same as the exponent for r. So if I want to know what an minus 1 is, that n minus 1 in the subscript gives us r to the n minus 1. And that n minus 2 in the subscript for an minus 2 gives us r to the n minus 2. And now we can just plug that into our formula. So there's our recursive formula. If we plug in those three expressions, we get r to the n equals 5r to the n minus 1 minus 6r to the n minus 2. Now, if that expression looks kind of familiar from your algebra days, it's a polynomial equation. Here we have an r instead of an x, but otherwise it's just like the polynomials back in the old days. And if you remember the types of techniques we use for solving polynomial equations, we put everything to one side of the equation and 0 on the other. So we have some polynomial on the one side and 0 on the other, and then we might factor it to see if we can figure out our solutions. So I'm going to go ahead and take our equation, move everything to the left. That means subtracting the 5r to the n minus 1 and then adding 6r to the n minus 2. And that's what we get. Notice that each of those terms has a few factors of r. We have n factors of r in the first one, n minus 1 factors of r in the second one, and n minus 2 factors of r in the third one. If we want to factor the same thing out of all of them, the most factors of r we can use is n minus 2. And when we do that, when we factor out n minus 2 factors of r from the first term, we get r squared. We get 2 more left over. We have n minus 1 factors in the second one. When we factor out n minus 2, we have 1 factor left over. And then the third term, that plus 6, is because we factor out all the factors of r, because it's r to the n minus 2. So that's great. So it's partially factored. Now let's go ahead and factor that r squared minus 5r plus 6. That's not so hard. We get r minus 2 times r minus 3. And now we have a completely factored polynomial. We can solve for r. We get r equals 0 from that r to the n minus 2. We get r equals 2 from that r minus 2. And we get r equals 3 from r minus 3. 3 solutions. And that gives us 3 possible sequences that are solutions to the recursive formula. Remember, our an was equal to r to the n, so we get 0 to the n, which is just 0. We get a to the n, that is the same as 2 to the n. And then we get an equal 2 to the n, and then we get an equals 3 to the n. So that r squared minus 5r plus 6 that we factored was really important. We're going to give it a name. We're going to call it the characteristic polynomial of this sequence. All the sequences that we're going to use this technique on have a characteristic polynomial that goes with it. All right, so we have 3 solutions. The question is, can we use those solutions to find more? Well, one way of we could try lots of different combinations, but one of it turns out the most effective way is to take each of those solutions, 2 to the n and 3 to the n, slap a constant next to it, so a times 2 to the n, b times 3 to the n, and then add those together, where again, a and b could be any constants that you could imagine, and then ask ourselves, do we get any solutions from those? Right? So we are taking, the fancy phrase is we're taking a linear combination of our solutions. Again, that's not something that you have to memorize, just letting you know what the language is on that one. So the question is, if we do that, does it work? In other words, is that a sub n going to give us solutions to our original recursive equation? Well, one way to find out, we have to check it algebraically, just like in that a few videos back. So we want to show that an is equal to 5an minus 1 minus 6an minus 2, or at least figure out when that's true. So let's see. So our formula says that an is equal to a times 2 to the n plus b times 3 to the n. If we put in n minus 1 instead, if we want to find out what 5an minus 1 minus 6an minus 2 is, we have to figure out what an minus 1 is. We just take our original formula and put n minus 1 instead. We need to know what an minus 2 is. We take our original formula and put in n minus 2 instead. All right, so let's go ahead and compute 5an minus 1 minus 6an minus 2 and see what happens. So we plug in for an minus 1. That was our formula for an minus 1. Then we plug in for an minus 2. That's our formula for an minus 2 that we're multiplying by negative 6. Now we use some of our old algebra tricks from what we've seen before. We use the distributive property to multiply the 5 through. We get 5a to the n minus 1 plus 5b times 3 to the n minus 1. We do that same thing with the negative 6 with the other one, minus 6a times 2 to the n minus 2 minus 6b times 3 to the n minus 2. And we've been in this situation before where we almost have those like terms. That 2 to the n minus 1 is almost a like term with 2 to the n minus 2. Same with 3 to the n minus 1 and 3 to the n minus 2. Fortunately, we know our little algebraic trick. We can steal one of the 2's out of the 2 to the n minus 1. That gives us 5a times 2 to the n minus 2. We can steal one of the 3's out of the 3 to the n minus 1. That gives us 5b times 3 to the n minus 2. And then we leave the other terms alone. Now we have 5 times 2 is 10, so that first term is going to be 10a times 2 to the n minus 2. 5 times 3 is 15, so we get plus 15b times 3 to the n minus 2. And again, we leave those last terms alone, and now we have like terms. So if we combine the 10a 2 to the n minus 2 minus 6a 2 to the n minus 2, that gives us 4a 2 to the n minus 2. If we combine the 15b times 3 to the n minus 2 minus 6b 3 to the n minus 2, we get 9b 3 to the n minus 2. And then we do our little trick where we say 4 is 2 times 2, 9 is 3 times 3. Combine all the factors of 2 to get a times 2 to the n. Combine the factors of 3 to get b times 3 to the n. And if that looks familiar, that's because it was exactly the formula for a sub n. So we just proved that a sub n is equal to 5 times a n minus 1 minus 6a n minus 2, which means that the formula a times 2 to the n plus b times 3 to the n always works as a solution no matter what our a and b are, which is going to make things really nice when we start finding particular solutions. All right, so now let's see if we can find the closed formula for an actual recursively defined sequence, including the initial terms. So we're going to say a0 equals 11, a1 equals 25, and an equals 5, an minus 1 minus 6, an minus 2 for all n greater than or equal to 2. All right, so the same recursive formula we had before. So we're going to guess an equals a times 2 to the n plus b times 3 to the n, which we already know satisfies the recursive formula. We just need to make sure that it works for the whole thing. Now, so we need to satisfy three properties in order for this to be an actual solution, right? We need to have a0 equal to 11. We need to have a1 equals 25. Those are our initial terms. And we need to satisfy the recursive formula. Now, that third condition about satisfying the recursive formula, we already know that works. We did a whole bunch of algebra showing that always works. So all we have to do is figure out how to make the a0 and the a1 work. So if we plug in n equals 0, 2 to the 0 and 3 to the 0 are both equal to 1, so we get a plus b for a0. And then we also know from our sequence that a0 equals 11. Put those together, we get a plus b equals 11. If we plug in n equals 1, we get a1 equals 2a plus 3b. That's just plugging into the formula. We also know from the definition of the sequence that a1 equals 25. And again, that gives us 2a plus 3b equals 25. Now, I'm not going to do the algebra to solve this system of equations. You have the algebra tools to do that. But if you were to do that, then you'd get a equals 8 and b equals 3. You can try that to see how it works. And since our an is equal to a times 2 to the n plus b times 3 to the n, we just plug in a equals 8, b equals 3, and we get 8 times 2 to the n plus 3 times 3 to the n as our solution, as our actual sequence. So let's sort of summarize what we did. So we have a sequence that has two initial terms, a0 equals c, a1 equals d. It has a recursive formula that is an equals constant times an minus 1 plus some other constant times an minus 2. We guess an equals r to the n. We plug that in to our recursive formula. We bring everything over, factor out everything that we can, and whatever remains, that characteristic polynomial, right, that r squared minus c1r minus c2, we figure out the roots. We figure out what happens when we set that equal to 0. So we take that equation, we factor it to get, I don't know, two values, r1 and r2, whatever those are. Our general solution that satisfies all the recursive formula is a times r1 to the n plus b times r2 to the n. We plug in our initial terms, our a0, that'll give us a0 equals a plus b, and a0 equals c, which means that a plus b equals c. If we plug in n equals 1, we get r1a plus r2b, and a1 equals d, that's from the definition, and then we set those equal to each other. Then we solve for a and b, our system of equations, just like we did before, and plug that into our formula for a sub n. All right, so I think you're ready to work on the activities. The PDF file is called Characteristic Polynomial.